All right, let's dive into one of the most powerful and honestly coolest tools in all of mathematics. Now, I know it can look a little intimidating at first, but I want you to think of it like a machine, a brilliant, powerful machine built for one single purpose, solving puzzles. When you really boil it down, a ton of complex math is just about finding the missing pieces of a puzzle. And usually, that puzzle starts out looking like a system of equations. So, take a look at this. Two equations, two unknowns. Pretty standard stuff, right? You probably have a few tricks up your sleeve from school. Maybe you'd use substitution or elimination, a little bit of algebraic shuffling, and boom, you've got your answers for x and y. No big deal. But what if we cranked things up a lot? What if you didn't have two equations, but 1,000, with 1,000 different variables? All of a sudden, those simple methods aren't just a little tedious, they're a complete nightmare. It's practically impossible to do by hand. We need a better way. We need a machine. And that, my friends, is where the matrix comes in. It's just a genius way of organizing all that messy information so we can work on it efficiently. So the first question is, how do we load our puzzle into this machine? Now, this might look a little crazy on paper, but stick with me. The process is actually super simple. It's a 3-step translation. First thing we do is just grab the numbers in front of the variables, the coefficients, and arrange them into a neat little block, making sure to keep them in the same order. We call this block matrix A. Okay, step 2, the variables themselves. The x and y, or whatever we're trying to figure out, they get their own special column. This is what we call matrix X, and it represents the unknowns we're hunting for. And for the third and final piece, we take all those numbers hanging out on the other side of the equal sign, the constants, and they form their own column. We'll call this one matrix B. And just like that, you see the pure elegance of this whole thing. Any system of linear equations, it doesn't matter if it has two variables or 2,000, can be neatly packaged into this one clean, beautiful equation. AX equals B. The puzzle is now loaded, and the machine is ready to go. So, our puzzle is in the machine. Now what? How do we actually get the answer out? Well, we don't use brute force algebra. No. We use something much, much cooler. We use a magic key. This key is called the inverse matrix. You'll see it written as an A with a little -1 floating up top. You can think of it like this. If our original matrix A is the lock on the puzzle, then this A inverse is the one-of-a-kind key that's perfectly crafted to open it. And once you have this key, solving the puzzle becomes almost laughably simple. To find our variables, our matrix X, all we have to do is take that inverse key, A inverse, and multiply it by our constants, B. That's it. One single clean multiplication gives you the answer to the entire puzzle. Okay, so that's obviously the big question, right? Where in the world does this magic key come from? How does our machine actually go about forging this inverse matrix? Let's pop the hood and take a look at the gears inside this thing. The process it uses has a bit of a fancy name. It's called Gauss-Jordan row reduction. But don't let that scare you. It's really just a step-by-step recipe for transforming our matrix. And the most incredible part, this whole powerful process only uses 3 simple moves. That's its entire toolkit. 1, you can multiply or divide any row by a number as long as it's not 0. 2, you can add or subtract a version of one row to another. And 3, you can just swap 2 rows. That's it. That's the whole playbook. So here's the game plan. It's kind of like a magic trick. We set up our matrix, our A, and right next to it we place this special thing called an identity matrix. Just think of it as a grid with ones going down the diagonal. Now, using only those 3 moves we just talked about, we start chipping away at our matrix A with the goal of turning it into that identity matrix. And as we perform those operations on the left side, the right side starts changing too. The moment our original matrix on the left becomes the identity, what's left over on the right has magically transformed into our key, the inverse matrix, A inverse. But hold on, before our machine starts grinding away and doing all that work, it has to run a quick but crucial diagnostic check. It has to ask one very important question. Can a key for this puzzle even be made? This check is called the determinant. It's just a single, unique number that you can calculate from the matrix. And that one number tells you everything you need to know. And the rule is dead simple. If you calculate the determinant and it's any number, literally any number other than 0, you are good to go. An inverse exists. The puzzle is solvable. But if that determinant comes out to be exactly 0, the machine hits the brakes. It means no inverse exists. The matrix is called singular, and it's a sign that this puzzle has some weird properties. Okay, enough with the theory. Let's see this machine in action. We're going to throw a more complex three-variable puzzle at it and watch it work its magic from start to finish. So here we go. A bit more of a mess this time with three variables, u, v, and w. But step one is always the same. We load it all up into our nice clean ax equals b format. Next, the machine just gets to work. It starts cranking through those row operations one by one, transforming that matrix. And then, look at that. What emerges on the other side is our perfectly forged 3 by 3 inverse matrix. The key is ready. And now for the best part, the final, satisfying payoff. We take our new key, A inverse, multiply it by our constants, B, and bam! The machine spits out the solution vector. Instantly, we have our answer. U is 2, V is 3, and W is 4. Puzzle solved. And look, this is so much more than just a clever trick for your math homework. As Siethakoza Ngema, the author of our source material, points out, this whole concept has massive applications across science, engineering, and technology. Seriously, this puzzle-solving machine is running silently behind the scenes of our modern world. It helps render the 3D graphics in your video games, it helps secure data online, it models everything from weather patterns to the economy. So the real question isn't just how the machine works, but what puzzle will you use it to solve?